In the previous video, you may remember that at the end we came up with these two numbers, and I said they were the same, right? But of course you saw when I was copying these that I cut off some digits. I just wanted to reassure you that was just because I approximated the square root of 3, and if you're dealing with computers you're always dealing with rounding anyway. Indeed, in actual fact, this was an exact answer. So now to round out this series about Gauss-Legendre Quadrature, I thought I'd show you a couple of things that you might be interested in looking at in the future, if this happens to be a topic that interests you. So we took a look at how to approximate functions between -1 and 1, right? And yes, that is indeed not an f. That's supposed to be an integral sign. And that's supposed to be the f. And we ended up solving a system of linear equations to determine, for the case that we knew 2 points, that we needed to know the values at f of -1 over the square root of 3 and f of 1 over the square root of 3. Right? Now you might ask yourself, well, what if we had 3 points? What f values do we need then? Right? Or what if we had 4 points? And it turns out that there is a series of polynomials that give us the answers. So these are called the Legendre polynomials. I should say it's a sequence, not a series. It's a sequence of polynomials. P1 of x is x, and P2 of x is 1/2 times 3x squared minus 1, etc. And you can derive all of these. But let's see what it is that the connection is between these polynomials and these points here. Let's take a look at this one, P2, because we had 2 points. That's 1/2 times 3x squared minus 1. Now what I want to do is I want to find out the zeros of this equation. So if I set that equal to 0 and I multiply through by 2, then I get 3x squared minus 1 is equal to 0, which means 3x squared is equal to 1. And x squared is equal to 1/3. And again, we have x is equal to plus or minus 1 over the square root of 3. So as it turns out, the zeros of this equation, or of this polynomial, the zeros of this polynomial, are just the points that you need to know on the curve. Now, another interesting thing about these Legendre polynomials, if we take a look at P1, if we want to know the zeros of P1, of course we set x equal to 0, and we see, well, x equals 0 is a 0 of it, of course. Now where have we seen that before? If you think about taking the integral of some function from -1 to 1, and using the midpoint rule, well, what is that midpoint? Well, the midpoint between 1 and -1 is just 0. So the point we would want and need to know for the midpoint rule is f of 0. So this gives us the point that we need to know for the midpoint rule, which is f of 0. And you may also remember about the midpoint rule that it was able, although we only had one point that we knew, it was able to exactly calculate the integrals of polynomials up to degree 1. And we've seen in the last few videos that if we have 2 points, we were able to exactly calculate the integrals up to degree 3. And it turns out this is a pattern. You take the number of points, let's call that n, and you subtract 1, and you get the degree of the polynomials that you can exactly integrate. Right? So if we had, let's say, 4 points, then we could exactly calculate all polynomials up to the 7th degree only knowing those 4 points. So again, it's pretty crazy. Now, if you look at these, you see P1, P2, P3, P4, and you wonder, is there a P5? Well, yes, there is a P5, and you wonder, well, how could I figure it out? There is a formula for that, and it was thought up by a guy named Rodrigues. The formula is 1 over, well, let's say it this way. The formula for Pi of x is 1 over 2 to the I times I factorial times the ith derivative of x squared minus 1 to the ith power. Okay, so again, that's pretty crazy. But let's do an example. We've just been dealing in the last few videos of the case that we had P2, so let's see if we can derive that. P2 of x would be equal to 1 over 2 to the 2nd power times 2 factorial, and then we would be dealing with the second derivative of x squared minus 1 squared. So if we simplify that, we get 1/8. Now let's just take the second derivative of this here. Well, let's take the first derivative. First of all, we'll use the chain rule. We get 2 times x squared minus 1. And then multiplied by the inner function, so it would be the derivative of the inner function, 2x. So that was the first derivative. We still need to take the derivative there again. Let's multiply this out. We get 4x times x squared, so we get 4x to the 3rd minus 4x. We still need to take the derivative of that, so we have 1/8, and the derivative would be 12x squared, right? Minus 4. So now we can just multiply this out. We have 12/8 x squared minus 4/8. So if we simplify that, we get 3. Oh, let's do it this way. 1/2 times 3, right? So that's just 3 2's, right? That's equal to 3 halves there. So I'm going to write it this way: 1/2 times 3x squared minus 1/2, because I'm wanting to factor out this 1/2. So 1/2 times 3x squared minus 1. So that's the answer we get for p2 of x. 1/2 3x squared minus 1. And now let's take a look back at these polynomials. And that is exactly what we had, right? 1/2 3x squared minus 1. So you see you can use this formula by Rodrigues to derive the Legendre polynomials. Now, one last question that you might have is, you might say, great, well now we know what points on the curve we need, because the zeros of these polynomials give us those, but we still don't know what the weights are. You'll remember back a few videos that we wanted to determine what this w and this v were in order to determine what our rule would be. So that is definitely something that you need to know, and there's also a way of figuring that out. So, and that is this formula here. I'm not going to prove these formulas here, just sort of give you an idea of what else is out there. So let's take a look at this formula here. Let's say it this way. The first time we ended up solving a system of linear equations, and we used v and w and v for those weights. So now let's just not say v, we'll just say w naught and w1, right? So let's see if we can derive this w naught from our first example. So w naught would be equal to 2 divided by 1 minus, now what were our points in our original example, right? When we know 2 points, you may remember that the 2 points on the curve that we needed were f of -1 square root of 3 over the square root of 3 and f of 1 over the square root of 3. Those were the 2 points we needed. And so we called this x naught. So, well, how about we just write that in here? X naught squared, although we see that that's x naught, so we can just go ahead and type that in there. X naught was -1 over the square root of 3 squared times, now we need the derivative of p2, because p2 is the Legendre polynomial that we need when we have 2 points, and that's the one that we just derived here, right? So I'll copy that from here. This is the one. So we just need to know the derivative of that for this equation here, right? So the derivative of that, let's say we want to know the derivative, that would be 1/2 times 6x, right? That would be it. So we'd have 3x, right? So that's the derivative. So we need to put in x naught here. So 3 times x naught was -1 over the square root of 3, and I need to square that whole thing, right? That's what this is right here. So let's see what that works out to. So we get 2 divided by 1 minus, well, -1 over the square root of 3 squared is just 1/3, right? So 1 minus 1/3 times, and what do I have here? I have negative, that's going to be here, right here, that's -3 over the square root of 3 squared, right? So square the top, square the bottom, I have 9 over 3. If we continue to simplify, we get 2 divided by 1 minus 1/3 is going to be 2/3 times 9 over 3 is just going to be 3. So we see that the 3's cancel here, and we have 2 over 2, which is 1, which, if you remember from the very beginning, those were exactly our weights. We had W was 1, we called it V, V was 1, x naught was negative 1 over the square root of 3, and x1 was 1 over the square root of 3. So if we wanted now to derive this one, which, as I said, we're calling, instead of V, we're calling W1, we're calling this W0, then we can see that if we put the positive value here, that it's not going to change anything, because it's always getting squared anyway. So we end up with the same answer. So those are just a few more of the more advanced topics that relate to Gauss-Legendre Quadrature. The Gauss-Legendre Quadrature. Not easy to say, but very nice to use.